Welcome back, lovers and haters of earth science. In our last episode, I left you with a bit of a cliffhanger. And I wanted you to see if you could figure out what our fourth weather factor is, created by our high and low pressure centers. And since I know the anticipation is killing us,
nope.
Let's get into this video. So the weather factor that's created by our high and low pressure centers is, drum roll please, wind. See, I told you we've all experienced it before. And wind simply is the horizontal movement of air due to different air densities, which is created by the uneven heating of Earth's surface. Because we all know that the temperature here in Malone, New York is definitely not the same as, let's say, Orlando, Florida. Now, in our last video, we discussed that wind always travels from high pressure centers to low pressure centers. But those pressure centers aren't always in the same location. So that means that our wind isn't always going to be coming from the same direction. Now, the way we determine which way the wind is coming from is by using what's called a wind vane. And this helps us to determine which cardinal direction that wind is coming from on any particular day. And something I need to note as well, it's very important to remember, ladies and gentlemen, that we always name wind where it's coming from and not where it's headed to. So if wind is coming from the north, it's a north wind. And if wind is headed to the west, it's an east wind, because that's the direction it's coming from. And one more thing I want to ask you about, because I know we've all experienced it before. How many of you out there have experienced different strength of winds? I'm sure it's every single one of us. Well, we can actually use our famous little isobars to figure out just how strong the wind is. So let's go ahead and take a look at how we use these isobars to determine wind strength. So wind speed, well, it depends on the pressure gradient. And a pressure gradient is simply the difference in pressure from one location to another location. So the greater the pressure gradient, or the greater the difference in pressure between two locations, the faster the wind will blow. And the lower the pressure gradient, the slower the wind will blow. So let me show you what this actually looks like. So the air pressures for City A and City B are shown at noon on Monday and on Tuesday. I'm going to be drawing an arrow between the two cities to show you the direction the wind was flowing each day. I'm also going to determine which day the wind speed was greater based on the pressure gradient. So let's start with Monday. Now on Monday, the wind is going to be flowing from City B to City A, because City B has a higher pressure than City A. Now on Tuesday, again, the wind is going to be flowing from City B to City A, because the pressure is much higher at City B than City A. Now on Tuesday, the wind speed is going to be much faster, because the difference between City B and City A's pressure is now 16 millibars. And that's how it works, folks. The bigger the difference in pressure, the faster the wind speed. Now, we actually measure wind speed using a device called an anemometer. And this is what an actual anemometer looks like. Now, we can actually determine the wind speed on a map by looking at the distance between isobars. So, the closer the isobars are together, that means that the wind is going to be much faster in that area. And the further the isobars are from each other, that means that the wind is going to be much slower in that area. So, if we look down at our map, this section right here is going to have the absolute fastest wind, because the isobars are very close together. And this section right here is going to have much slower wind speeds because those isobars are much further apart. So let's go ahead and test your skills now. And you tell me, where will the wind be the fastest on this map? So 10 seconds on the clock. Ready, go. So if you said right here, you are amazing. Because remember folks, the closer the isobars are together, the stronger the wind will be. Aw, yeah folks, we're blown right through this video. And we only have 3 more things to talk about. Coastal breezes, monsoons, and then finally we have to figure out how the heck we're going to show all these weather factors on a weather map. So let's start with coastal breezes. Now, a coastal breeze is created because of the difference in specific heat of land versus water. And specific heat is simply the amount of the sun's radiation that it takes to heat up a specific substance. And land and water are very different. So I have an example that I hope most of us can relate to. So you go to the beach on a real hot summer day. And you get to the sand and you finally take your sandals off. And then your feet start to melt from the insane heat. So what do? Well, you run to the water and sweet, sweet relief. And there you have it, folks. The difference between the specific heat of land versus water. So now let's go ahead and take a look at what that actually means for coastal breezes. So a sea or an ocean breeze is during the day, and the surface winds will blow from the water towards the land. And the reason? Well, as we discussed earlier, the warmer air is definitely going to be over the land, which will make it a lower pressure. And the cooler air is going to be over the ocean, which will make it a higher pressure. And as we all know, winds always flow from high pressure to low pressure. Now at night, those surface winds, they shift, and we get what's called a land breeze. So the surface winds will now blow from the land towards the water. And the reason is that now the cooler air is over the land because it cools down much faster, and the warmer air is going to be over the ocean because it cools much slower. So now our pressure systems have switched. So the high pressure is over the land and the low pressure is over the ocean, which will cause the winds to flow from the high pressure to the low pressure. And this phenomena, folks, it actually affects the overall climate of specific areas on Earth, which we call monsoons. Now, a monsoon is a seasonal reversing of winds and precipitation patterns caused by large differences in temperature of the land and the ocean water in certain seasons. And here, folks, is an image of that change. This is the same exact location during 2 different times of the year. So we're actually going to go ahead and look at India because India is actually affected by this monsoon weather pattern every single year. So during the summer, heavy rains occur when moist wind flows from the ocean to the land, or our sea breeze. And during the winter, dry conditions occur when dry wind flows from the land to the ocean, our land breeze. And now, folks, it's time to answer the question on no one's mind. Wait a minute, that's not right. I mean everyone's mind, which is how the heck do we show all these weather factors on a weather map? Well, guess what? We use these little doohickeys right here. And these little doohickeys, they have a name, which is called a station model. And a station model is a simple diagram that represents 10 important pieces of weather information in a specific area. And the best part, folks, is that you can find this beautifully explained station model right at the bottom of page 13 in your Earth Science reference table. And before we get into the big explanation, I need to note one thing. Station models do not have units on them, folks. it's something you definitely need to remember. And now let's break these station models right down. So let's go ahead and break down our simple station model. Now the first piece of evidence, this right here, is the air temperature. And it's always in degrees Fahrenheit. But remember, on our station model, we have no units. Next up is this little asterisk right here, which is the present weather and the type of precipitation that may or may not be occurring. After that, we have this half symbol right here, which is the visibility, and it simply means the distance you can see in miles. So for this particular station model, we can see a half a mile away. Next up, we have this number right here, which represents the dew point temperature, again in degrees Fahrenheit. After that, we have these two tails right here, which represent wind speed in knots. Now, the total number of feathers changes dependent upon the weather, but a whole feather is equal to 10 knots, and a half feather is equal to 5 knots. After that, we have this stick, which actually indicates us the wind direction. Now, the stick points in the direction the wind is coming from. Because remember, ladies and gentlemen, we always name winds on where they're coming from and not where they're going to. Next on our list is this number right here, which represents precipitation. And this is the amount that occurred over the last 6 hours. Almost there, folks. So this number right here represents the barometric trend, which is the change in air pressure over the past 3 hours. Now, the actual change is 1.9 millibars. And if you look, a plus or a forward slash is equal to rising barometric pressure. And if you have a minus or a backslash, that means falling barometric pressure. And finally, the last thing we need to be aware of on our station model is the barometric pressure, this number right here, which represents the air pressure of a specific area. However, it's abbreviated. So the actual air pressure here is 1019.6 millibars. Oh, almost forgot, ladies and gentlemen, this circle in the center actually represents the amount of cloud coverage in a specific area. So the percent of the circle that's shaded in, that's covered in clouds. And in this particular station model, 75% of the visible sky is covered with clouds. And now let's go ahead and take a quick look at how we abbreviate our air pressures to put them on our station models and convert our abbreviated air pressures back into actual air pressures. So the barometric pressure on our station models is represented by a 3-digit abbreviation. Now, to convert the actual air pressure into an abbreviation, we need to follow a few simple steps. First, we need to take off the 9 or the 10 in the front of our actual air pressure. Then finally, we simply remove the decimal and remove all other units. So let's take a look at these two examples. So 978. All right, remove the 9, remove the decimal, and remove the units to get an answer of 870. Okay, let's try one more. So, remove the 10, remove the decimal, and remove the units to find our air pressure abbreviation is 104. Okay, so now let's go ahead and reverse the steps. And we're going to convert our abbreviated air pressure back into our actual air pressure. So again, we follow a few simple rules. If the abbreviation is greater than 500, we add a 9 to the front. And we put a decimal between the last two numbers. And then finally, we make sure to put our units back in. So 870. Well, that's definitely higher than 500, so we're going to be adding a 9. Then we need to put back our decimal between the last two numbers and add our units. And guess what? Our actual air pressure is 987.0 millibars. Okay, so now we need to follow a few different steps. So if the abbreviation is less than 500, we need to add a 10 to the front, a decimal between the last two numbers, and our units. So 104, definitely less than 500. So we're adding a 10, we're putting a decimal between the 0 and the 4, and we're adding our millibars to get an actual air pressure of 1010.4 millibars. Okay, so let's do a few more to make sure that we're actually getting this. So for these examples, we're going to take our actual air pressure and we're going to turn it into our station model abbreviation. All right, first one, 998.8 millibars. All right, remove the 9, remove the decimal, and remove the units to find out that our station model abbreviation is 888. Okay, another one. So 1016.5 millibars, remove the 10, remove the decimal, and remove the units to get our station model abbreviation of 165. Okay, let's go ahead and do one more. So 976.8. Remove the 9, remove the decimal, remove the units to get a station model abbreviation of 768. Okay folks, so now I want you to try the next two on your own. So make sure to pause when I say and figure out what the station model abbreviation is for the next two air pressures. Ready? Go. All right, so now we're going to go ahead and we're going to take our station model abbreviation and turn it back into an actual air pressure. So let's look at the first one, 001. So the question we need to ask ourselves, is it larger than 500 or is it smaller? Well, I'm pretty sure we all know that 1 is much smaller than 500. So we need to add a 10. All right, make sure to put our decimal in between the 0 and the 1 and add our units back in to find our pressure of 1000.1 millibars. All right, let's do one more together before you do a few on your own. So again, let's look at our station model abbreviation, 082. So is it greater or less than 500? Well, in this case, it's still less. So that means we're adding a 10. We need to make sure to put a decimal between the 8 and the 2 and add our units, which is millibars, to find out that our pressure is 1008.2 millibars. All right, folks, now it's time to test your skills. So what I want you to do when I say is pause the video and solve what the actual air pressure is for the next three abbreviations. Remember, if it's larger than 500, we're adding a 9. And if it's less than 500, we're adding a 10. All right, ready, go. Well, I'll tell you what, folks, the weather forecasters, they better be worried because we're coming for them. Because not only do we know all the factors that affect weather, but we also have a nice, neat, tidy way to show all of those weather factors on a weather map. And I think it's time we blow this episode out. So, as always, complete all your additional assignments, and I'll see you on the next episode of Earth Science 2020.